Hi class, welcome to another session on biomaterials. So we have been discussing our second unit, which is metallic and ceramic implants. So the next metal or alloy that we are going to discuss is the cobalt chromium alloy. We've already discussed the stainless steel. So cobalt chromium alloys are of two types: the castable one and the wrought one, which is produced by hot forging. So castable one is the cobalt chromium molybdenum alloy, and hot forging, the wrought one, is cobalt nickel chromium molybdenum alloy. So castable cobalt chromium alloys are used in dentistry, and they have also been recently used for making artificial joints, whereas the wrought cobalt nickel chromium molybdenum alloys are used to make the stem of the hip and the knee prosthesis. So when I say the stem, I mean the tail part of the implant that is actually used to fixate the implant to the bone. Right, so this tail part goes inside your bone and fixates the prosthesis, so that the prosthesis would replace the head of the bone. So the cobalt chromium alloys that are recommended for surgical implant by ASTM, which is the American Society for Testing and Materials, there are four recommended alloys. One is the cobalt chromium molybdenum alloy, which is F75 ASTM number. Then the wrought cobalt chromium tungsten nickel alloy, which is F90. Then the wrought cobalt nickel chromium molybdenum alloy, which is F562. And then the wrought cobalt nobelium chromium molybdenum tungsten and iron alloy. Right, quite a lot of quite a few metals here, which has an ASTM number of F563. So these are the four types of cobalt chromium alloys that are recommended for surgical implants. Now the cobalt and chromium in the cobalt chromium alloys form a solid solution with up to 65% of cobalt. Right? Molybdenum is added to increase the strength after casting or rotting, but this happens because molybdenum has got finer grains when produces finer grains when it is added to the alloy. So that's why it will increase the strength when the metal is rotted or when the alloy is rotted. So cobalt nickel chromium molybdenum alloy contains approximately 35% cobalt and nickel, equal cobalt and nickel, and it is called as MP35N. This like the ASTM name. So this alloy is highly resistant to corrosion under stress, and when it is exposed to seawater. So seawater has got a lot of chlorides in it. We know seawater is very salty. We wouldn't want to drink seawater if we are thirsty, right? So our body fluid is also equally corrosive. It has got equal number of chlorides and fluoride ions that are floating around in the interstitial fluid. So the body fluid is equally corrosive. So if an alloy can can resist being corroded in seawater, then it can sustain in human body. That's what is the analogy. So that's why cobalt nickel chromium molybdenum alloy is like very suitable for using in the human body. Then cold working is like it's a technique of making implants out of metals. So cold working significantly enhances the strength of this alloy, but making prosthesis while making larger implants in when the during with cold working procedure is very complicated. So if you want to make larger implants, unfortunately you'll have to slightly compromise with the strength, but hot forging is the best method to do so. So, though the mechanical properties of cobalt, nickel, chromium, molybdenum alloys are similar to that of cobalt, chromium, molybdenum alloys, they are not used to make bearings for surfaces of joint prosthesis because of their poor frictional properties. We know that joints undergo, like any implant in the joint, will undergo a lot of friction because it is the juncture of two bones, right? So the joint is mobile. So every time the joint moves, the bone is going to have the bone is going to experience certain friction, and so would the implant. So if the implant is made up of a material that doesn't tolerate friction very well, that wears off with friction, that corrodes with friction, means it is not suitable for making joints. And that is why cobalt, nickel, chromium, and molybdenum alloys are not. I mean, the combination of this is not used for making surfaces of joint prosthesis. So They have superior fatigue resistance and they have ultimate tensile strength. They've got very, very good tensile strength, and that's why cobalt, nickel, chromium, and molybdenum alloys are suitable for application that would require long service without any fracture or stress. So if you take an implant, then stem of that implant is probably the best place to use cobalt, nickel, chromium, and molybdenum alloy, because that is not this wears off with friction. So obviously you can't use it in the head of the implant. So if you use it in the stem, it is going to be stable there, and it is very, very strong, and it doesn't succumb to fatigue. So it can give a very good base to the implant, right? It can solidly support the implant. It can weight bear with the weight bearing capacity of this alloy is very, very good. So it can definitely support the joint function. So again, wear, corrosion, and fretting often release metallic products, which we know, and these metallic products are toxic to the implants and the organs. So particulate cobalt is very, very toxic to the human body. However, particulate chromium and cobalt chromium alloys are very, very tolerant, very, very tolerant. So cobalt as such is toxic, but the alloy is not toxic. That's what they mean to say. And then the metal interacts in vitro with indicated cobalt and nickel extracts at 50% concentration, and they appear to be very, very toxic in 24 hours. However, cobalt extract seems to be less toxic than, sorry, chromium is less toxic when compared to nickel and cobalt. So the Young's modulus of cobalt chromium alloys does not change with change in tensile strength, and this can be very effective when it is used in weight bearing joints. So that's all we have for this lecture. We shall discuss titanium based alloys in the next one. Thank you very much for your time.